And we're back. Welcome back and happy Thursday. Today we'll continue on with our discussion of the Poisson distribution, and the focus of today is on the mean and the variance for the Poisson distribution. But before we begin, we'll focus first on some administrative bits. The reading due by November 3rd, section 3.4.5, pages 65 through 67. It's not a lot, but please make sure you're keeping up with the reading. Also, Project 3, the reliability simulation, is due this evening at the usual 1 second before midnight. Please do not wait until the last minute to submit your project, and make sure what you're going to submit runs before you submit it. Verify that. All right, so last time we met, we talked about this instrumentation to monitor the number of customers that enter a store and leave a store. And we used that to motivate the idea of the Poisson distribution, which deals with the arrival of events in time. We looked at the Poisson configuration and coined a rate as the average number of observations across a set of standard modules of observations delta t. We derived an expression for the probability mass function for the Poisson distribution. That's probability of observing x many events in a module of observation is equal to e to the minus lambda, where lambda is the rate, times lambda to the x power upon x factorial. And so we use the Taylor series to demonstrate and prove that the law of total probability holds true for this Poisson probability mass function. So it is, in fact, a proper probability. And so we need also to show the summary statistics, because showing the total probability is not enough. We need the mean and the variance. So let's jump right into that. So for the mean, of course, a reminder, here's the probability mass function for the Poisson distribution. And we set up what the mean is, the expectation. So we have the probabilistic weighted sum for all values x. X goes from 0 events observed in time, 1, 2, 3, up to infinity. We have x times the probability of that x. And we want to show that that's equal to lambda. So let's set this up. We have our expression for the expectation, the mean, mu. And we're going to plug in for what p of x is. So we have the sum, x goes from 0 to infinity, x e to the minus lambda times lambda to the x upon x factorial. Okay, so now we make the observation that this e to the minus lambda does not involve x, the index of our summation, anywhere. For all intents and purposes, it is a constant, and we can factor that out from that summation. So we write that out front, e to the minus lambda, our infinite sum, x goes from 0 to infinity, x times lambda to the x upon x factorial. So now we take our factorial term in the denominator, and knowing that the factorial is just x times x minus 1 times x minus 2 dot 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 times 2 times 1, we're going to factor out one of the terms from that factorial. The remaining terms is just x minus 1 quantity factorial. So if we do that, we notice then we get a copy of x in the numerator, a copy of x in the denominator, and these x's are going to cancel. They're going to go to 1. So we do that with that cancellation, and then we get the following expression, e to the minus lambda times our infinite sum, x goes from 0 to infinity, of x times lambda to the x over x times x minus 1. And of course, we do that cancellation. Now, one observation we can make before we do that cancellation, let me take a step back, is that we make the observation that for the case where x is equal to 0, well, we have a leading x here. And that leading x, when that x is equal to 0, that's going to be 0 times something else. And 0 times anything is always 0. So we can rewrite this expression based on the sum for x goes from 1 to infinity instead of 0 to infinity, because that first term is going to be 0. And so we get this new version, and now we do that cancellation. We have a copy of x in the numerator and x in the denominator. They cancel, and they go to 1. Okay, so this gives us the following version of the expression. We have e to the minus lambda, what we had before, and our infinite sum from x goes from 1 to infinity of lambda to the x upon x minus 1 quantity factorial. And so now we're going to take this lambda and we're going to factor out one of these lambdas. So lambda to the x is lambda times itself x many times. So we're going to factor out one of them. That gives us lambda times lambda to the x minus 1. So now this lambda that we factored out, that's a constant underneath the summation that does not involve the index of the summation x. So we're going to factor that out. That's going to give us lambda times e to the minus lambda out front. And then we have what's left, that infinite sum. X goes from 1 to infinity, lambda to the x minus 1 upon lambda upon x minus 1 quantity factorial. Okay, so now we're going to make a change of index. We're going to say let y equal x minus 1. And so here's x. If I'm going to replace it with y, that's y equals 0. And then here, this is x minus 1. I'm going to replace that with y. And down below in the denominator, that's x minus 1. I'm going to replace that with y. So our new equivalent expression, mathematically, is just lambda e to the minus lambda times the summation turns into y goes from 0 to infinity, lambda to the y power upon y factorial. And so when we talked about the Maclauren series for e to the x, or e to some power, is just the infinite sum from y goes from 0 to infinity, that power to the y over y factorial. Well, we have exactly that, the Maclauren series of e to the lambda. So we're going to replace this summation with e to the lambda, and that gives us our leading lambda times e to the minus lambda that we had from before, times e to the lambda. There's our replacement. The e to the lambdas, they cancel out because that's e to the minus lambda, e to the plus lambda. That's just e to the lambda minus lambda, e to the 0, which is just 1, and that gives us lambda. Okay, so now we've just proven that the expectation of a Poisson distribution is lambda, which is the range. Okay, and there's our results. So let's go on to the variance. The variance is a little bit more complicated, but it's doable, very doable. We'll go over it in steps. And so here's the expression for the variance. The variance, sigma squared, is just the expectation of variable x, that Poisson variable, minus its mean quantity squared. So let's plug in for expectations. So here's our expression, x minus mu quantity squared. We're going to multiply by p to the x, by p of x. And p of x, again, is the mass function, as we said before, for the Poisson distribution, e to the minus lambda times lambda to the x upon x factorial. Now, we can use an expression to help us called the variance equation. It's a shortcut for solving what the variance is. And I direct you to this video. It's a well-known result. I'm not going to prove it here, but I encourage you to look at the video to see where it comes from. No tricks, just a little bit of algebra. And so this variance, we can substitute the following expression when we solve for the variance. The variance is the same as e, the expectation of x squared, minus e of x quantity squared. Well, we know what e of x is. We solved that before. We said that's just lambda. So we have part of our variance, it's just lambda squared, because that's e of x is lambda, and we square that, so that's lambda squared. Okay, so now what we need is this expression. We need this e of x squared in order to complete our proof for the variance of a Poisson distribution. So you can use this, but we're going to see that's a little bit wonky to do so, and we're going to do something else to make it easier for us. And so if we set this up, this variance equation, well, we know that E of x, the expectation is lambda, so we have this term all squared away. That's just lambda squared. Now we'll look at E of x squared, the expectation of x squared. So we plug in for expectation, that's the probabilistic weighted sum, so we have x squared times p of x, where each value x goes from 0 to infinity. Well, if we do that, we plug in what p of x is, the Poisson probability mass function. We get x squared e to the minus lambda times lambda to the x upon x factorial. So this is kind of hard to cancel out the x squared using this x factorial because this is squared. If this were x, we could peel out one of the factors multiplied together for this factorial in the denominator and cancel out. But this is kind of hard to do, so we're going to try something else. And so instead, what we're going to do, instead of this e of x squared, we're going to try something that's a little bit different from e of x squared, expectation of x times quantity x minus 1, and then we're going to take that result, fix it up to give us an equivalent expression for this e of x squared. So let's do that. Well, if we do this e of x times quantity x minus 1, which is a little bit different from e of x squared, well, you multiply this x by everything in the parenthesized expression. That's the same as e of x squared minus e of x. Okay, so that you notice here is going to give us some result, but in part of that result, we have an e of x squared. And so we're going to use an identity from this setup to give us an expression we can use to substitute for e of x squared. Okay, so let's do that. And so if we do this expectation, well, we have our function x times x minus 1, and we multiply that times p of x, which is probability mass function here of the Poisson distribution, e to the minus lambda times lambda to the x upon x factorial. Okay, so now when we do that, well, we know the following happens. For the case of the summation where x is 0, well, we have 0 times something, right? 0 times anything is always 0. And for the case of the summation where x is 1, we have 1 minus 1 is 0, right? So that's 0 times other stuff around it. 0 times anything is 0. So that means for the first 0th term and for the first term, for x equals 0 and x equals 1 for the summation, both of those terms are going to be 0. So we can rewrite this expression accounting for the x equals 0 term and the x equals 1 term of the summation both being 0. And so this summation is going to change. It's going to start for x equals 2 because x equals 0 and x equals 1 are both 0. And so now we have the infinite sum from x goes from 2 to infinity of x times x minus 1. That hasn't changed. And here's our p of x, e to the minus lambda times lambda to the x upon x factorial. All right, so now what we're going to do is we're going to look at this factorial, and we're going to peel off 2 of the terms for this factorial. So we're going to peel off the x term and the x minus 1 term, and what's left is x minus 2 quantity factorial. Now, if we do that, well, we rewrite this expression. We have x times x minus 1 times x minus 2 factorial in the denominator for what used to be x factorial in the denominator from the Poisson's probability mass function. And so this infinite sum, we have an x times x minus 1, e to the minus lambda, lambda to the x power upon x times x minus 1 times x minus 2 quantity factorial. So, of course, we have an x in the numerator, an x minus 1 in the numerator. We have an x in the denominator, x minus 1 in the denominator. So this x and x minus 1 are going to cancel with this x and x minus 1. It's all going to go to 1. And so this leaves us with the infinite sum for x goes from 2 to infinity, e to the minus lambda, lambda to the x upon x minus 2 factorial. And so now we're going to make an observation here. We know that this lambda is multiplied by itself x many times. If we peel off 2 of those factors multiplied with one another, we can actually do some interesting renaming of the index of the summation to help us get our solution. And so we're going to take this expression and we're going to factor out this e to the minus lambda because it's a constant underneath this summation. And then for what remains, well, we look at it and say, okay, well, let's factor out lambda squared. So this becomes lambda squared times lambda to the x minus 2, because exponents add, upon x minus 2 quantity factorial. And then we have that leading e to the minus lambda in front of the summation that we factored out because it doesn't involve the index of that summation. So it's a constant, and we can bring that out of the summation. Okay, so now we have this expression, and we make another observation. This lambda squared, that's a constant underneath the summation. It does not involve x, the index of the summation, anywhere. So we're also going to factor out that lambda squared. So that gives us lambda squared, e to the minus lambda, times our infinite sum. That's x goes from 2 to infinity of lambda to the x minus 2 power upon x minus 2 quantity factorial. So now we're going to make a change in the index of the summation. We're going to say, let y equal x minus 2. So here we see the bottom bound of the index of the summation, x is equal to 2. So if we replace it with y, it's going to be y is equal to 0. Okay, that should be a y. Y is equal to 0. And then here we have an x minus 2, so we're going to replace that with y. Here we have an x minus 2 for the factorial. We're going to replace that with y. So now if we make those substitutions with our change of index variable for the summation, it becomes lambda squared e to the minus lambda. Well, that hasn't changed, that leading coefficient from before. We have the infinite sum, and now infinite sum for y goes from 0 to infinity, lambda to the y upon y factorial. And so going back to the definition of the Maclauren series, well, this summation, infinite sum, is nothing more than the Maclauren series for e to the lambda. So we replace that with e to the lambda, and that gives us our leading coefficient, lambda squared e to the minus lambda, times e to the lambda, which is nothing more than just lambda squared because it's e to the minus lambda plus lambda. Those exponents are going to add for those e's when they're multiplied together. And so our result there is lambda squared. So now that we have this result, we know that this lambda squared is equal to this result of this expectation. And so if we say, all right, well, our e of x times quantity x minus 1 is expectation of x squared minus x, and we just solved that this is all lambda squared. So now we're going to do a little bit of algebra, right? We're going to do a little bit of algebra, and we said we were going to do this expectation and fix it up. So if we fix it up, well, if we actually do out this expectation here, that's expectation of x squared minus x, well, the sum of the expectations is the same, expectations of a sum is the same as the sum of the expectations, so that's equal to e of x squared minus e of x. Okay, so we just said that this whole expression is equal to lambda squared. So we replace this with lambda squared, and we get e of x squared minus e of x is equal to lambda squared. Okay, well, if we add e of x to both sides of the equality, now we get an expression, e of x squared is equal to e of x plus e of x plus lambda squared. Well, e of x, we said before, is just lambda, so we have e of x squared is equal to lambda plus lambda squared. And there's our result for e of x squared. And now we can use the variance equation. All right. And so we have now e of x squared is equal to lambda squared plus lambda, or lambda plus lambda squared, doesn't matter because addition is commutative. And we're now going to use that as a substitution in our variance equation. So there's our variance equation, and we just solved e of x squared is lambda squared plus lambda. And then we know that e of x from before is just lambda. We square that, so that's lambda squared. And we get this variance is equal to lambda squared plus lambda minus lambda squared, which is just lambda. And that's our result for the variance of a Poisson distribution. And so we have now the mean of a Poisson distribution is lambda, which is the rate parameter. And the variance of a Poisson distribution is also lambda, which is the rate parameter. And so the Poisson's mean and variance are the same as the rate. Last time, when we had the previous module, we developed an expression for the probability mass function for the Poisson, and we showed the relationship between the binomial distribution and the Poisson, namely the large sample limit. And so this completes our study on the Poisson, and later on in the semester, we'll have another module where we'll use this to do some interesting modeling and make some data-informed decisions. So with that, that's all I had. We are finished our module on the Poisson, and as usual, please make sure you're keeping up with the reading. I look forward to seeing your solutions for Project 3, and as usual, please stay healthy, stay safe, and have a great weekend, and I'll see you all on Tuesday.